The symbol for an ideal independent current source connected between terminals A and B is shown on screen. It consists of a circle with an arrow inside it. The arrow gives the direction of current flow through the source, and the value of the source is shown as J of t and is written right next to the source. It is customary to show the current I of t flowing through the source to be in the same direction as the arrow, which is given as part of the symbol, and the voltage, following the passive sign convention, will have the polarity as shown on screen. The most important property of an ideal independent current source is that the value of J of t is given or is known, which is also equal to I of t and may be equal to a value, for example, 5 amperes. The voltage V of t can have any value and depends on other components that may be connected to the current source. If we plot this characteristic on a graph where we show I of t on the x-axis and V of t on the y-axis, since the current is constant, it will give us a characteristic which is a vertical line, and it crosses the x-axis where I of t is equal to 5 amperes. The voltage can have any value. Once again, the main characteristic of an independent current source is that the value of the current is given or is known, and the voltage across the source can have any value depending on what else is connected to the source. This was an example of a DC current source which did not change with time. Next, we will look at an example of an AC current source where the value of J of t changes with time, for example, is equal to 5 sine of t. For t is equal to n pi, where n is an integer, the value of the source will be equal to 0. For t is equal to 2n pi plus pi by 4, the value of the source will be approximately equal to plus 3.5 amperes. For t is equal to 2n pi plus pi by 2, it will reach its maximum positive value and J of t will be equal to 5 amperes. And so on, the value of the current source is given for different time instants. If we were to plot this characteristics on a graph, the value of the source is changing with time, and at t is equal to 0 or n pi, the value is coinciding with the y-axis or the vertical axis. We will denote this as the characteristics at t is equal to n pi. At t is equal to 2n pi plus pi by 4, it has a positive 3.5 amperes, again a vertical line at 3.5 amperes, and this is the value at t is equal to 2n pi plus pi by 4. And so on, we can plot the characteristics as a function of time and as shown on screen in the plot of I versus V of t. Once again, the key characteristic of an ideal independent current source is that the value of the current is specified or is known, and the value of the voltage across it can have any value depending on what else is connected to the current source. When the value of the current source J of t is equal to 0, then the characteristics looks like the following. If we plot I of t on the x-axis, V of t on the y, it consists of a vertical line which coincides with the y-axis, where the current is equal to 0 and the voltage can have any value. This is the same characteristic as a resistor of value infinity or an open circuit, and hence a current source of value 0 is the same as an open circuit, and we show the open circuit by simply drawing two nodes with nothing connected between them as A and B. The voltage V of t of the current source and the current I of t follow the passive sign convention, hence the power absorbed by the source will be given by the product of voltage and current, V of t multiplied by I of t. And also this will be defined as negative of the power supplied by the source. The source that we have defined so far is an ideal current source, and its characteristics is a vertical line where we have I of t on the x-axis, voltage on the y-axis, and the source has a vertical line. For example, for a constant DC current source, the value may be 5 amperes. This ideal source is absorbing power in the first quadrant and is supplying power in the fourth quadrant. A real voltage source will have a slightly different characteristics such that when it is absorbing power, the voltage across it increases and the current increases at the same time, whereas when it is supplying power, the current decreases as the voltage across it is increasing in magnitude.